Hello, my name is Daniel Lissus, and I'm presenting our work on heading estimation using ultra-wideband received signal strength and Gaussian processes for the IROS 2021 online conference. Let's start with the general problem setup. We have a planar robot in a room with a given area it's allowed to drive in. Consider, for example, a Roomba or a warehouse delivery robot. Now, in order for this robot to navigate and execute tasks autonomously, it needs to be able to estimate its position and heading, which is shown by this red arrow. In this work, we focus specifically on heading estimation. Mathematically, the heading is defined as the relative orientation of the robot body frame B to the world frame A. In this simple initial state, these frames are aligned. As the robot moves, its body frame orientation relative to the world will change. Our goal is to estimate the changing heading value as the robot goes about its tasks. Although our particular work focuses on heading estimation, knowing the robot position is also needed for automating indoor robots. For indoor applications where GPS cannot be used, a common approach uses ultra-wideband or UWB technology. A classic setup consists of a UWB tag mounted on the mobile robot and several stationary UWB anchors at different heights around the room. Here, 3 are shown for clarity. However, in our work, we use 5. The robot's position is determined by measuring the range or distance between the UWB tag and each of the UWB anchors. Knowing enough of these range measurements allows to position the UWB tag to decimeter level accuracy. This setup is also frequently combined with an IMU to get even better performance. As we will see, this exact technology can also be leveraged to predict the heading estimate without any additional hardware. Speaking of heading estimation, let's now consider why this problem is still an actively ongoing area of research. A typical modern robot setup will involve an IMU sensor with a gyroscope. Heading estimation is possible by only using gyroscope measurements for dead reckoning. However, it is widely known that dead reckoning starts to drift as there's no way to correct the accumulating errors. This plot is taken from a real-world experiment and shows how the absolute value of the error grows. This is made worse by the fact that the gyroscope has no information about the world frame and thus is unable to correct for initial errors. So this approach is not robust. The next 2 approaches use the gyroscope to dead reckon and correct it using another sensor. One such option is to use a magnetometer to measure the local magnetic field. It is then possible to estimate the heading by comparing the assumed constant local magnetic field and the magnetometer measurement. Using a magnetometer to correct the gyroscope prevents drift and corrects initial errors, as can be seen in this plot. However, in reality, indoor settings are not as cut and dry as what is shown in our diagram. Metallic objects such as tables, shelves, pipes, and even other robots can cause the local magnetic field to be far from constant, leading to unreliable estimation. The last approach we'll present is to correct the dead reckoning using position measurements. This can be done by adding in the UWB setup that we previously presented. However, the shortcoming of this approach is that the heading is still unobservable when the vehicle is moving with constant linear velocity, including times when it is spinning on the spot or is stationary. This can be seen in the simplest stationary case by considering the range measurements to the tag. Despite the orientation clearly changing, the measured range would still produce the same values. Nonetheless, there are other measurable quantities in positioning systems which have been used to deduce the heading. Particularly, a work by Gross empirically calibrated a relationship between the received signal strength and the angle of arrival of a GPS receiver. Used with a gyroscope prediction step, they were able to deduce the roll and pitch of their UAV. Dotlik and the UWB company Decawave used a UWB module with 2 antennas to analytically derive a relationship between the difference in received signal phases between the antennas and the angle of arrival. Finally, a work by Ledergerber was able to achieve position and orientation estimation by coupling wheel odometry and a learned relationship between the UWB channel impulse response and the robot's orientation. Our work attempts to provide a simpler approach by only making use of the received signal strength of UWB modules and avoiding empirical or analytical derivation to aid in generalizability. Let us first consider antenna radiation patterns. The UWB modules use antennas to communicate between each other. Each of these antennas has a unique radiation pattern around it, which is largely defined by the antenna type. Here, Two radiation patterns are shown for a simulated ideal dipole and an ideal helical antenna. Let's look at what is actually happening in these plots. The radiation pattern is actually a measure of the antenna directivity, measured in dBi, with respect to the angle around the antenna. This pattern extends in all three dimensions. However, we're only showing it in 2 dimensions for clarity. Now, the reason we're interested in this directivity is because it affects how strong the signal being received or sent will be. On the receiver end, this signal strength is termed the received signal strength, or RSS, and an example RSS plot is shown on the right from one of our data sets. The key point here is that the directivity is a function of the angle, and the RSS, a measurable value during runtime, is a function of the directivity. Thus, it can be concluded that the RSS is also a function of the angle. The caveat here is that the RSS is also a function of a number of other factors, such as the range between the two antennas, various losses, and etc. Let's return back to our original positioning problem setup and now make explicit note of the radiation pattern. Considering just one anchor, we now measure not only the range, but also the RSS value. If we move this anchor around the robot while keeping it at a constant range, we note that the RSS value will change even while the range one will not. We are thus able to gain heading information by measuring the RSS. When we have multiple anchors, each of them can provide some information about the overall vehicle heading. Looking at these RSS values from our various anchors, we can then infer that some inverse relationship exists between the heading and the respective range and RSS values. However, it is very difficult to derive this relationship analytically. The matter is made even worse when we consider that in practice, our Euler angle representation is undesirable due to the discontinuity at pi and negative pi. So, we're actually interested in estimating 2 quantities, the sine and cosine of the angle. We do this to get our desired direction cosine matrix parametrization of the heading, which is an element of the special orthogonal group SO2 and is unique for all physical orientations. So we have these 2 desired relationships that we wish to get. The analytical solution is too complex. Instead, the approach that we are going to take is to implement Gaussian processes. A Gaussian process is something that models a distribution over functions. Mathematically, we can write one of our desired functions g as a Gaussian process with some mean and covariance, also called the kernel. The way to shape this distribution to correspond to our desired function is to condition it based on some known inputs and noisy outputs. Note that our inputs can be multidimensional, while our corresponding output is a scalar value. This modeling process can be broken down into 3 sections, here shown on a toy problem. First, we apply some prior knowledge to the problem. We take the prior mean to be 0 and choose the square exponential kernel, both of which are common choices. Next, we group the tunable parameters of this kernel into a general hyperparameter theta and also estimate some noise value on our measured outputs. This whole process is shown in the following plot, where we show some true function in black and the sampled prior functions in various colors. The shape of the prior functions is defined by the prior mean, the kernel selection, the initial hyperparameter selection, and the noise. Next, we condition this prior. We collect a set of training inputs and outputs, as well as some test inputs. We wish to get the test outputs corresponding to our test inputs. This can be done by conditioning the test outputs on the test inputs, as well as on the training inputs and outputs and the hyperparameters. As we can see, the mean function now resembles the true function. Finally, we also train the model. This is done through maximizing the likelihood of the probability that the training inputs generate the training outputs, given the hyperparameters. Graphically, this training can be seen to improve both the mean and the uncertainty estimation on our function. Our proposed approach is then as follows. In order to get our desired SO2 state, we wish to model the sine and cosine of the Euler angle heading as a function of the RSS and range measurements from 5 different anchors. Knowing that these relationships are too complex to model analytically, we model them as Gaussian processes, which we train using some collected training data. These Gaussian process predictions can then be combined after normalization to produce a valid SO2 heading estimate, which we denote Y. In order to improve the performance of this estimate, we use it as a measurement step in an invariant extended Kalman filter, or IEKF. This filter, which is comprehensively presented and proven in the Barreau and Bonnabel paper listed here, is a version of the extended Kalman filter, which allows estimation to be performed directly on matrix Lie groups, which for us means directly on our SO2 state. As such, we use the gyroscope dead reckoning prediction step with our GP estimate as a correction step in this filter to produce our overall estimated SO2 state. For more information on the exact implementation of the IEKF in our approach, please refer to our paper. This method is validated using 3 datasets collected in our lab. We used the POSIX developer tag and the creator anchors, which are pictured on the right. One dataset was collected manually by moving and rotating the UWB tag on the ground, and 2 others were collected on a ClearPath Husky mobile robot, which can be seen in the photos. An example of one of our Husky dataset trajectories is also pictured. The manual dataset and the Husky datasets each had their own training sets to validate the approach. The manual dataset collected up to 200,000 training points, whereas the Husky one collected up to 86,000. The 3 tests that were run ranged from 90 to 800 seconds. First, let's consider the Gaussian process prediction results in isolation. As a reminder, these plots are the 2 desired relationships that we wish to learn in order to predict our SO2 heading. As can be seen in the plots, an overall relationship is learned, although the RMSE and the uncertainty is still relatively high, as can be seen in the chart on the left. For this reason, we combine the estimate with a gyroscope prediction step in an IEKF. In order to evaluate our full filter performance, we compare it to a couple of the other heading estimation methods we mentioned earlier. The plot here shows the absolute value of the heading error produced by all methods on one of the Husky datasets. First, the pure dead reckoning prediction suffers from drift as explained earlier. We run dead reckoning from both perfectly and imperfectly initialized conditions to fully show the lack of initial error correction. Next, we also used an onboard magnetometer to produce a heading estimate, which we used in an identical fashion in an IEKF. We ran 100 Monte Carlo simulations with initial conditions randomized about the true initial heading and plot the average results here. As can be seen, the initial errors are easily corrected and drift is prevented. Finally, we also plot our proposed method with a gyroscope prediction and a Gaussian process correction, similarly run for 100 Monte Carlo simulations. Although the performance is slightly worse than the magnetometer IEKF, initial errors are still corrected and no apparent drift is visible. Further filter results and consistency can be seen in the following plots. The plot at the top shows the errors from all 100 Monte Carlo runs for our filter and the corresponding uncertainty bounds. Right below it is the Mahalanobis distance, another common consistency metric, with the corresponding average and 99.7th percentile values. Finally, the bottom plot compares the various estimators and their uncertainties from the same initialization point. As can be seen in the table summarizing our results, our method produces a heading estimate within 10 degrees of accuracy, which is comparable to the performance achieved using a magnetometer IEKF. Since the magnetometer IEKF would still likely use a UWB system for positioning, our approach effectively achieves comparable performance while using one less sensor for a position and heading estimating indoor robot system. Additionally, the magnetometer IEKF actually performs far worse than our method in the manual dataset. We hypothesize that this is due to this dataset placing the UWB tag on the ground and in close proximity to the pipes and other metallic objects below the floor. This likely made the quality of the magnetic field calibration and the corresponding filter estimates much worse. In conclusion, our work shows the feasibility of predicting heading estimate as a function of range and received signal strength measurements of a UWB system using Gaussian processes. We then implement this Gaussian process estimate in the correction step of an invariant extended Kalman filter. This filter is then able to produce heading estimation within 10 degrees for a real indoor vehicle with only a typical positioning setup of a gyroscope and UWB. This means that heading estimation is now possible without any additional hardware. I would like to thank the Canadian Foundation for Innovation, the FRQ&T Team Grant, the NSERC Discovery Grant, and McGill University's William Dawson Scholar Program for their support of this work. Thank you for your attention.